In this lesson, we're going to learn about solving differential equations that require separating the variables. We have already done this a little bit before, but we're going to go and see some more challenging problems. I just snipped this from your book. This is just saying what the general form of these separable differential equations are. M of x is simply one of the terms or a part of our diffie-q that is solely in terms of x. N of y is a part of our differential equation that's solely in terms of y. Of course, we have dy dx and then equals 0. Now these can look very different, but the general idea is that x and y, or whatever two variables we're using, are sort of intermingled. We want to get all of the one variable on the left, so all of the y's and the dy on the left, and then all of like the other variable, usually x, and the dx on the right. And then that way we can integrate both sides, one with respect to y, the other x. Here are three differential equations that can be separated. So we're going to go through each one and take a look at the algebra required in order to write it with the variables separated. So if we take a look at this top equation right here, I'll rewrite it down here. We have x squared, so that's our m of x, plus 3y, that's our n of y, times dy dx equals 0. And then we sort of want to think ahead a little bit, a couple steps. So remember, the goal is to keep everything with y in it on the left side and everything, in this case, with x in it on the right. So actually the first thing I'm going to do is not multiply by dx because I have a couple terms over here. I want to actually subtract x squared from both sides. So we'll have 3y dy dx equals negative x squared. Now from here we can multiply both sides by dx, which will give us 3y dy equals negative x squared dx. And voila, our variables are now separated. Please note that we haven't solved this differential equation. We have simply rewritten it so that it's able to be solved by integration. Our next one, we have some trig functions here. We also see a different notation for dy dx, which is y prime. I prefer the Leibniz notation, so I'm going to rewrite that as dy dx. I just prefer it because since we are separating the variables, it's helpful to sort of see them literally separate here. And so we can also see that we don't really have anything with y in it. We have just most things with x. So I'm going to divide both sides by the sine of x. So we'll have dy dx equals the cosine of x divided by the sine of x. And then we realize that cosine divided by sine is cotangent of x. Multiplying both sides by dx in order to fully separate our variables will give us that dy equals cotangent of x dx. For this last differential equation, we again want to rewrite y prime as dy dx. So I'm going to have x, and yes, it's going to look like a complex fraction, but that's okay. So from here, we want to keep everything with y in it on the left-hand side. Note that the things with y in it are the e to the y plus 1. That right there is sort of a package deal here. I can't really separate and subtract 1 from both sides because it's part of this like mathematical expression and it's also in the denominator. What I really need to do is simply get this x on the right-hand side. Now this x is in the numerator, so I can multiply both sides by 1 over x or simply just divide by x on both sides. And what that will do is it will have dy dx, which this dx is really in the denominator, times e to the y plus 1. And remember, we divided both sides by x, so it went away on the left-hand side. And then on the right, we have 2 over x. Now at this point, I can multiply both sides by dx, so I'll end up with the e to the y plus 1, still in the denominator. And on this side, I'll have 2 over x dx. So now my variables are separated and we would be ready to solve by integrating both sides. So just as a quick recap, we have so far simply done some algebra in order to separate variables to get a differential equation prepared to be solved through integration. We have not solved the differential equations yet. We've simply used algebra in order to rewrite with the variables separated. Now let's actually find a general solution of a differential equation. We can clearly see that this diffeq right here does require the separation of variables that we just have done. So here's our diffeq. And I want to get everything with y in it on the left first. So the first thing I'm actually going to do, I'm going to do two things at once, really. We want to get this y over here, and we want this x squared plus 4 over here. So we need to divide both sides by y and both sides by x squared plus 4. So that'll give us the dy dx still over here, but we had the 1 over y because we divided both sides by y. On the right, we had the x already, and we divided both sides by x squared plus 4. From here, it's pretty simple to see that we just multiply both sides by dx. So we'll have 1 over y dy equals x over x squared plus 4 dx. So now we've separated our variables and we're ready to integrate. So now we can integrate. So the integral of 1 over y dy is the natural log of the absolute value of y. Then on the right side, we can see that we can use a u substitution over here. So if we let u equal x squared plus 4, then our du would be 2x dx. Now we don't have 2x dx, we just have x dx, so I will divide both sides of this by 2. So rewriting this integral, again, I haven't integrated yet. We'll have the 1/2 out in front. The x squared plus 4 is u, and then the x dx gets replaced with 1/2 du, so I'll put this as 1 du. Now from here, we can just integrate. We actually, once again, have a natural log. So we will have the natural log of the absolute value of y is 1/2 the natural log of the absolute value of u. I'm just going to go ahead and back substitute. U is x squared plus 4. X squared plus 4 is always positive, so no absolute value sign necessary. And of course, plus c, I'm going to call it c sub 1. At this point, we should probably start looking ahead a little bit as we're solving differential equations and finding either general or particular solution. Well, I guess general solutions. And we don't automatically just have y equals in part of our answer. We have to do some algebraic and mathematical manipulation to get y equals. Either way, this c value is not going to be the same one at the very end. So I'm going to call it c sub 1 because I am going to do a little bit of manipulation to it. And so it's not technically the same value. Now we do have natural log on both sides here. I'm going to use the power property to show this 1/2. I'm going to bring it up as an exponent, so it's really the square root in there. So we have the natural log of the absolute value of y equals the natural log of the square root of x squared plus 4, since it's the 1/2 power, and then plus c sub 1. Now here, if I want to get the stuff out of the natural logs, I can just do e to each side. So I'm going to have e to this side and e to this side. And remember, e to the natural log of a cow is a cow. So on this side here, we just have the absolute value of y, which can actually just get dropped, so long as we put a plus or minus out in front. So we will see that in just a second. I also just want to point out this is e to the a plus b, which is really e to the a times e to the b here. And so I can really write this as e to the c sub 1. And then I had this plus or minus the square root of x squared plus 4. Now, this plus or minus can really go all the way out front, and plus or minus e to the c sub 1 is just a general c value. So we have y equals c times the square root of x squared plus 4. I don't want to make this video super long, but I do encourage you to check your work. I did take this directly from your textbook, and as we can see here, they showed how you can check your work. This was just the original differential equation that required the separation of variables. And so for y over here, you can see that they plugged in exactly what we got for y, right over here. Now for dy dx, they simply took the derivative of y to get with respect to x. So just as a quick, so this is our answer. But if we take the derivative with respect to x here, right, this is really c times x squared plus 4 to the 1/2 power. So we bring the 1/2 out in front. So we'll have c times 1/2, and then this will end up getting raised to the negative 1/2, which means a square root in the denominator. Using the chain rule, we'll multiply by 2x, and the 2's will cancel. So that's why I ended up getting the cx over the square root of x squared plus 4 here to plug in. So these two blue things are what they plugged in. And then when we take x squared plus 4 to the first divided by x squared plus 4 to the 1/2, we subtract 1 minus 1/2, and we end up getting the x squared plus 4 to the 1/2 here. So the differential equation checks out when we plug in this function y. So the solution checks. This function is in fact a solution to the original diff-EQ. So now let's find a particular solution. This is just going to have us solving for c. So again, this is not anything really that new. We're just practicing more. But we do now have a separable differential equation. And so this one looks a little bit more complicated. The dy and the dx are actually already separated, which is kind of interesting. And our initial condition we'll use in just a minute, but it's right here. So getting started with this, we want to see how can we separate our variables. We kind of have a lot going on. Oh, and it's equal to 0. So I'm going to first actually subtract this term. I know there's still a y in it, but it has an x and a dx in it, so I'm going to get that over to the right-hand side. So now from here, what we can do is divide both sides by this guy right here. So when we, so we'll get that with x in it, so we'll divide both sides by e to the negative x squared, e to the negative x squared. And so what we'll have left is y squared minus 1 dy equals negative x y, and then since this is in the denominator with a negative exponent, it should just be in the numerator with a positive exponent. Exponent rules for the win. Then our very last step is to divide both sides by y. That'll get all of our y's over here. So dividing by y will cancel over there. So let's see what we have. We have now separated our differential equation. We've done the separation of variables, so we can now integrate each side. This should just be broken up, so this is y squared over y minus 1 over y. Y squared over y is just plain old y. So we have the integral of y minus 1 over y dy, so it's a pretty simple integration. On this side, it looks like we can do a u sub. If we let u be x squared, that should work out pretty nice. So we'll let u be x squared. Du would then be 2x dx, and so 1/2 du is that x dx that we have there. I'll just bring that negative out in front to alleviate that issue. So inside here I'll have e to the u, and then my x dx gets replaced with that 1/2 and then a du here. So it's not too bad of an integration here on either side. On the left here, using our power rule, and then our natural log. And then over here, the integral of e to the u is just e to the u. U is x squared. And then, of course, our plus c. I'm going to, again, call it c sub 1 for reasons I've talked about previously. Now, from here, I'm going to actually plug in, actually, I should not have probably made that c sub 1. It doesn't really matter. C and c sub 1 are the same idea, but I almost forgot what we were doing. We're going to plug in for a particular solution. So we want to find c. So our particular solution is right here. So I'm going to plug in 0 for x and 1 for y. So that's what's going to happen down here. So let's plug in our initial condition. Again, our initial condition was this. It was y of 0 equals 1. So plugging into this equation here, every time I see a y, I'm going to plug in 1. So I have 1/2 times 1 squared minus the natural log of 1, which we know what that is. Then for x, I'm going to plug in 0, and then plus c. So these are nice values. This gives us 1/2. The natural log of 1 is 0. E to the 0 is just 1. Be careful here with solving for c. A lot of us will get to a situation like this and then get the wrong answer for c. This is like the simplest part, but that's why it's so easy to mess up. We're going to add 1/2 to both sides to get that c is 1. So now our final answer is simply just plugging into the solution that we found, but plugging in 1 for c. Now, in general, it looks nicer to have just whole, well, not whole, but integer coefficients for everything. So if you multiply everything through by 2, you will just have y squared minus, let's do it. Let's just multiply through everything by 2 to make it look nice. So we can do that because it's an equation. So we'll have y squared minus 2 ln of y, using the power property. It's the natural log of y squared, and now I no longer need the absolute value, equals negative e to the x squared. And then 2c is really just the same as c. And what am I forgetting? I'm forgetting to plug in what c was. How could I be so silly? So here we go. C is 1. We just found it. So it should end up being plus 2. And there we are. This is one that is almost impossible to get y equals just because of how it is. So we're just going to leave it as is here. Okay, in order to keep this video as short as I can, I'm going to move through these fairly quickly. So if any of these look like ones you want to get some practice with, that's fine. I'm going to actually solve each one of these without walking through every single step, but I will show the solutions here in just a moment. If you'd like just some practice, go ahead and pause the screen and practice working these out. I will then show the solutions. Here are the solutions to parts A and B. Just a quick note on part A. After I integrated, I wanted to just have nice whole values in front here. When we have both variables squared, it's kind of harder to solve for just one of them without a square root and a plus or minus. So essentially this is like a conic shape, like this is an ellipse, I believe. I'm not quite sure off the top of my head. I should know, but either way, what I wanted to do was just get the x and the y on one side. Getting to this point is great. Really, it's just about writing things in a nicer way. Then for part B, we have going from log form to exponential form, and then it was a negative y, so we just had to slightly rearrange the final solution here. All right, going into part C, I just wanted to make a quick note that y prime, I would highly recommend that when you're doing separation of variables that you rewrite it using the Leibniz notation, dy dx, the other variable is x here, it usually is. This one didn't require a whole lot in terms of separation other than just multiplying both sides by the dx. This is something that has thrown us though a little bit with integrating. So when we integrate, when I'm integrating y, it's y to the first, so I can use my integration power rule here. But then over here, if you'd like to do a u substitution, you can, because our inside function here is pi x. So the way to do this would be let u be pi x, and then du is simply pi dx. Now remember, pi is just a number. Okay, it's not a variable. And so I can just have 1 over pi du equals dx, because here I don't have anything but dx here to replace. So I'll replace the dx with 1 over pi du. That 1 over pi can just go out front. So I'll have 1 over pi times the integral, the sine of u du, and then it's fairly simple from there. That's not totally necessary if you can just see that you need to multiply by the 1 over pi to sort of compensate for that on the inside with the chain rule, if you did check by taking the derivative. So on this side here, when we integrate sine, we'll get negative cosine. So that negative I'll just bring out front, and then it's the cosine of u. U is pi x. So what I was saying there before about the chain rule is if you were to find the derivative of this, the cosine of pi x, with all this, you would definitely have to multiply by a pi out in front. And so this 1 over pi takes care of that, which we didn't have. Then on the left-hand side, we still had the 1/2 y squared. So in order to make these coefficients here look a bit nicer, what I'm going to do is multiply through by 2 pi, since that'll get rid of those fractions there. So if you multiply everything through by 2 pi, it'll make it look nicer. So we'll have pi y squared equals negative 2 cosine of pi x plus c. I realize that pi is not an integer, but nor a whole number or anything nice, but it just looks better than 1 over. So that's how we can write it real nice. Here in part D, this one was a pretty straightforward separation of variables. We just wanted to multiply both sides by dx and then multiply both sides by 5y cubed. No natural logs here. There was no like 1 over anything to the first. It was just the power rule for integration a few times. Then if we want to keep going with making things look nice, we have a 4 and a 5 in our denominators here. Their least common multiple is 20, so I'm going to multiply everything through by 20. When I multiply that by 20, 20 over 4 will cancel to 5, so it'll be 5 times 5, so we'll have 25 y to the 4th equals 40 x, and then we'll have 4 x to the 5th. Now, again, I don't need to write 20c. I can call that c sub 1, and then this is just c. It represents 20c sub 1. For these last two here, these are similar to some of the book problems, but we'll note that they're almost the exact same differential equation, except this one has theta on the right-hand side and this one has the variable t. So doing our separation of variables is going to look a little bit different for each one. So for part E, I want to multiply both sides by dt, but then also divide both sides by either just theta or 0.3 theta. It's really up to you. I am just going to divide them by theta instead and leave the 0.3 on the right. That way I'll have 0.3 and then just dt. Again, up to you. You'll get the same answer overall in the end. So now when we integrate, we're going to have the natural log of the absolute value of theta. That looks cool. Equals 0.3t plus c sub 1. Again, theta is like our y here, so I want to get theta equals. I know it's a little bit strange, but that is what we want to have our function, like theta equals here. So from this point, I can go to exponential form, so I'll have e to the 0.3t and then plus c sub 1. We've seen this enough times now. That would be times e to the c sub 1, so that'd be c e to the 3t equals our theta. And again, we can drop the absolute value just because e to the anything, any positive number to the anything is always positive. Now, if we look at part F, this one's actually a little bit simpler. So in part F, on the right-hand side, we have the variable t. So there's not as much rearranging here. We're just going to multiply both sides by dt. So now when I integrate, I'll have theta equals, no natural log. Then I can use the integration power rule. Now from here, that is super messy. Just mathematically, you never want to leave an answer looking like this. Not only is there a fractional coefficient, it's a decimal in the numerator, like, ugh, gross. So we definitely don't want to do that. In my head, I'm sort of thinking, like, how do I want to handle this? I'm just thinking now, I'm thinking spur of the moment here. I just made these up. So 0.3 is 3/10. So I'm going to rewrite 0.3 as 3/10. And then I still had the 2 in the denominator. Just roll with me here. Then this is really 3 over 20 t squared plus c. Now at this point, I already have theta equals. If I were to multiply everything through by 20, that is an option. I'd have 20 theta equals 3t squared plus c. There's alternate ways to write this. Like, this is fine by me because I have theta equals, but if we did want to multiply everything through by 20, an alternate way of writing this, and if we wanted both variables on the same side, I could definitely do this. And again, c is the same as 20c is the same as 20,000c. It just represents a generic constant. So there you have it. Either one of these would be appropriate ways to write your final answer for this one.